Welcome back. Let's continue with our lecture on general theory of relativity. Today we are going to talk about Einstein Tensor. This is one of the important topic directly connected with the Einstein's equation. In this lecture we define Einstein Tensor and note some of its important properties. Today we are going to talk about Here we list some of the useful tensor identities. So let G denotes determinant of metric tensor, that is determinant of GAB lower indices. The determinant of upper indices would be 1 by G because they are inverse of each other. We have a simple expression which connects the determinant and epsilon ijk. So we have G is equal to 1 by 24 epsilon ijkl epsilon pqrs gip gjq gkr gls. This is what we have listed in one of the tutorials. So we have already seen this expression. So we can go ahead further multiply it by epsilon ijk and simplify it to get one more identities, where we have a determinant G is multiplied by epsilon pqrs, and then other side you have epsilon ijk and the various metric tensor. One of the interesting properties here is that metric tensor also can lower and raise the indices including epsilon ijk, even if it is not a tensor in a true sense, but once you multiply by determinant of G or square root of determinant of G, it would become a tensor. So we will not get into all that. So one of the identity is to show that the differential dg determinant of metric is given as G, the determinant itself, into GAB upper multiplied by dg GAB. So D here is a differential operator. You can differentiate with respect to coordinate variable, or you can take exact differentiation. So this is a standard identity of matrices you might have come across, but nevertheless I am not going to show this. It's fairly straightforward to show using this and then using some of the straightforward properties of this. Now, of course, this is the exact differential. You can also differentiation with respect to coordinate variable. It's a partial differential with respect to coordinate variable. Then you would see that this would takes the similar form, except that dg is replaced by the partial differentiation with respect to coordinate. This our notation we have used dc is equal to d by dxc. That is a shorthand notation we have been using. Now once we have this identity, we can show some of the simple properties. One of them is a property of connection or Christoffel symbol with the contracted upper and lower indices. It's a symmetric in the lower indices, so you could contract with any of the lower indices and an upper indices. It turns out that it can be simply written as 1 by square root of minus g dxa into square root of minus g. So minus g essentially comes from the determinant of Lorentzian space-time, or the pseudo-Riemannian space-time would have a negative sign, and that need to be incorporated when you take the square root, and that is why that minus sign is appearing. So otherwise in the case of Riemannian space, it would be just a square root of g. It is easy to show this. Similarly, we can again multiply by gbc to this such that this would have the contraction between the two of the lower indices. That would be what is done by multiplying by GC. So this is equivalent to gamma A CC or something like that, that would lead to confusing notation. So instead of that, it would be written like this, and that can be also written as a differential of a determinant of metric and the metric tensor itself. This is something similar in this line, and it is also possible to show it in a straightforward way. The next important expression is the divergence of a vector field. That is, A is an arbitrary vector field, and whose divergence, that is taken the covariant differentiation and that contracted with respect to the indices, and that is what we call is a divergence of a 4 vector, and that simply can be written as a partial differential with respect to A and then square root of minus g into your vector A. Divergence of a vector field is a very important quantity. You may see that it often comes in the various form. In the electromagnetism, you have seen that the divergence of electric field, which would give the source charge, in absence of charge it would be simply 0. The divergence of magnetic field is also 0. It shows the absence of charge. So that is not in 4 dimension. However, when it is done purely in terms of the Riemann geometry, this square root of minus g won't be there. It is just a square root of g. You can do it in 3 dimension. Then you can have a divergence of electric field, magnetic field can be written in terms of a gradient of this simple quantity, which would be useful to show the Gauss law and related theorem. In the case of 4-dimension pseudo-Riemannian space, you will have a square root of g and then the gradient taken with the pure partial differentiation. So these properties would be very useful. Now we go ahead and redefine or remind what is a Ricky tensor. We have a Riemann tensor, which is a RABCD. The last index is the upper index. That is how we have defined. These places of the indices have to be kept here because of various symmetry properties. Now we see that indices B and D can be contracted because they are symmetric. We know that once we lower D, we see that the AB together with CD can be interchanged, and that we could contract Riemann tensor in the B and D, because that would lead to non-zero, non-trivial result. If we contract with the A and B, that would give rise to 0, because we have seen that the Riemann tensor is an anti-symmetric in the first 2 indices. Anti-symmetric tensor has no trace, or all the diagonal elements are 0. So that is why when you contract with GAB with respect to AB would give rise to 0, and same is true for the C and D. Now you B and D and A and D you can contract, giving rise to non-trivial result. However, one has to careful to define them, otherwise you will end up having a minus sign. In our case, we are contracting between the B and D, not A and C. So the resulting second rank tensor, which is a symmetric tensor in indices, which is called the Ricky tensor. Usually it is pronounced as Ricci in the Italian spelling. So RAC, which is given as GBD, RABCD. So this is what we call is a Ricci tensor. From looking at itself, we can make out that it is a symmetric straight away from the properties of Riemann tensor. And let us go ahead that since the Ricky tensor is a symmetric tensor, we could go ahead and construct a scalar by simply contracting the indices A and C, and that is what we call is a Ricci scalar, or simply call it a symbol by R, contracting the Ricky scalar, that is R is equal to GAB RAB. So this gives simply a scalar which we call the Ricci scalar. Now we sometimes also call it simply the scalar curvature. That is what we have in the case of sphere, you could see that has a value of a positive r square. The curvature is given in terms of r square, and in the case of a negative sphere, you will have a minus r. For the flat space, again all these quantities are 0. Minkowski space, you have a RABCD is 0, RAC is 0, Ricky Tensor is 0, and the Ricky scalar is also 0. Now we have another interesting thing which we have already seen about the space-time symmetry and so on. We have 3 spaces which are completely or maximally symmetric. This can be listed as a Minkowski space which has a 0 curvature, and then we have sphere in n-dimensional sphere which has a positive curvature and which has a constant positive curvature, and the second is a negative sphere which has again constant negative curvature, and all these things come under the interesting case of constant curvature, and they are classified into 3 things. We will more exploit this into cosmology when it comes to positive, negative, and 0 curvature space. Let's continue with the Riemann curvature and some of its important properties. We have seen the definition of Riemann tensor, and we know some of the symmetry properties of Riemann tensor. Here I am going to introduce you one of the important property which is called Bianchi identity. For that, let's recollect properties of simple properties of Riemann tensor. So definition of Riemann tensor is given in terms of first derivative of Christoffel symbol and the product of Christoffel symbol. That is why it is non-linear. Here is where the non-linearity comes in because of the product of Christoffel symbol. Christoffel symbols are again expressed in terms of derivatives of metric tensor, and that is why we have a Riemann tensor can be expressed in terms of a second derivative of metric tensor, and there is also product term which makes it non-linear. So we know some of the symmetry properties of Riemann tensor. It is anti-symmetric in the first 2 indices. Anti-symmetry denoted by square bracket, that is, if you have a tensor, second rank tensor AB, and square bracket indices AB, implies that we have half into A into AB minus A into BA. So if the tensor is anti-symmetric, then we have AB is equal to AB. So that is same way we can have a symmetry property which is defined in terms of the round bracket. That is not what we are dealing now. So we have a anti-symmetry in the first 2 indices. When we lower the last indices down here, we get A, B, C, D, and then we also know that the last 2 indices also have a property of anti-symmetry, that if you interchange them you end up with the minus sign. In the compact notation it is represented by this. Okay, let's go ahead with the last symmetry property, that is the lower indices. If we group first 2 and last 2 indexes, then interchange them, that Riemann tensor is symmetric about this operation, that you combine them and interchange them, and that is going to be symmetric. So summary of all this, Riemann tensor has this interesting property that you fix the first indices and cyclically permute last 3 indices B, C, D, and then you would add them up, and that would give rise to 0. So it can be simply shown using this property, these 3 symmetry properties of a Riemann curvature tensor, and in short you can write it like this. Now comes the important Bianchi identity. It is given by derivative of a Riemann tensor, lower indices with the A, B, C, you cyclically permute these three indices, that is A going to B, B going to C, and C going to A, and then add them up, and that is going to be 0. Now it is easy to show this identity. However, it is involves very long algebra, because of the long expression for Riemann tensor can be shown explicitly by substituting this. However, there are easier methods. One can use the anti-symmetry property of covariant derivative to write the Riemann tensor, and then you differentiate that again, and then you can show that that is going to 0. So it is can be shown through that. In both cases it is algebra, however straightforward but long algebra. You can show that the derivative of a Riemann tensor, and then cyclically taken the permutation and added them up, it's going to give you 0. So this identity is what we are going to use further to define what is called the Einstein tensor. Of course, from the name itself, it is that the Einstein who first found significance of this tensor, and also probably defined this tensor. So in order to understand Einstein tensor, we state its important property first, and that can be obtained straightforward from the Bianchi identity. In order to show what should be the Einstein tensor, we start with the Bianchi identity, that is a covariant derivative of a Riemann tensor. Take first three indices and cyclically permute them and add them up, going to be 0. Now we contract various indices, but however we have to be careful. If we don't choose our indices carefully, that's going to be 0 because of the anti-symmetric properties of Riemann tensor. Once don't give a 0, result is contracting the indices A and D and B and E. So A and D and B and E, so they are chosen such that it gives some meaningful result. In order to see this, let's write it down. So we are basically multiplying by GAD, GBE to this Bianchi identity, and then we can try to simplify each term and see what do we get. So this stage it is straightforward. We rearrange each term to get the meaningful result. Let's rearrange the first term. We have rearranged and renamed the dummy indices or smart indices. So to have A and D and B and E. So this is such that B and E contraction gives us a Ricky tensor, and then this would simply give the divergence of Ricky tensor. Now the next one is also renamed. Again it is B and E and A and D. It is going to be same. So we are going to essentially get the 2. The last term is a contraction between the B and E and A and D. So it's only involves Riemann. Of course there is a C here, but that we can see, but it would simply give us the Ricky scalar. So once we see that, we get Ricky tensor here, the same term again, and then we have a divergence of R. So this is what we get. We can rewrite this neatly by dividing by 2 on both sides. Other side is 0, so it doesn't really matter. So we have a GAD, divergence of RCD, and then half times derivative of Riemann scalar, or that is covariant derivative of a scalar is also a partial differential, but we can keep the notation. Now we rewrite nicely. We see that below we have a divergence of Ricky tensor and half times GAB into divergence of Ricky scalar. All in all, we can write it as a divergence of RAB minus half GAB into R. So you see that the tensor inside has a divergence 0. So this basically taking the divergence. So it's a second rank tensor which is called the Einstein tensor, which has a 0 divergence. That seems to be the important property of a Einstein tensor, or rather Einstein recognized this to be the important property of this combination of Ricky tensor. Einstein tensor, which is usually called GAB, is given as a RAB minus half into GAB into R. That is called the Einstein tensor and has a 0 divergence. Again, we list some more useful identities. Again, it is you can show them, or I might ask them in some of the tutorial, or even in some of the tests. You are well versed with doing the tensor algebra. The first one is a divergence of a symmetric tensor. AIK is a symmetric tensor whose divergence is given as a 1 by square root of minus g, the partial differential of AKI square root of g minus half AKL, partial differential of a metric tensor. And this is somewhat important and useful. We see that we have already seen the Einstein tensor has a 0 divergence, and that means that looking at the definition of Einstein tensor, which is given as a GAB is equal to RAB minus half GAB into R. So this is symmetric, which is a Ricky tensor, and then this is metric tensor, which is also symmetric. So Einstein tensor has to be symmetric. So from that perspective, it is just this of Einstein tensor is 0. But we have seen that from the Bianchi identity. However, if you want to take the divergence of a symmetric second rank tensor, you could use this tensor identity. Again, because the relation between the covariant and contravariant, you can write it in terms of covariant component instead of contravariant component here, and then you have a plus is replaced by minus. So this is the same identity, but it is slightly rearranged. You can show them, but I am not going to show this identity. Now let's look at the divergence of anti-symmetric tensor, that is FIK. FIK is a standard name used for anti-symmetric tensor in the respect of anti-symmetric tensor, which comes in the electromagnetism, or which we call it the Maxwell tensor. Of course, it is not Maxwell tensor. Any anti-symmetric tensor could have this property that whose divergence can be simply written in terms of the partial differentiation. The anti-symmetric property here seems to help to get rid of this extra term, and then you have a pure partial differential defining the divergence of the anti-symmetric tensor. So this is also a very useful property. And then last identity is about the box operator acting on the scalar. The box operator is a two covariant differentiation and contracting with respect to the indices A and B, and that is what we call is a wave operator. So that in terms of a partial differential can be written in terms of this identity. It's also very useful if you can't remember the Laplacian any generalized coordinate, you could use them. This is a partial differential, this is the determinant of metric, and then you have this expression. With this you can express the Laplacian in any coordinate system. In the 3 dimension, it reduces to simply Laplacian. In 4 dimension, it becomes a wave because there is a minus sign, and then higher dimension you can have them. This is how it can be defined in terms of the partial differential, and that would help to simplify, reduce the equation. Here is an example. Let's show that RABCD is given as a k into GAD GBC minus GAC GBD, then k has to be constant. It seems to be an interesting Riemann curvature tensor, which can be purely written in terms of the metric tensor. All the constraint we get here is that the k has to be constant. So that is what we have to show. Let's see how do we go about showing it. First, let's start with the expression for the Riemann tensor given in terms of the metric tensor. Now, next step is to calculate the Ricky tensor. We calculate the Ricky tensor by contracting the Riemann tensor, that is multiplying by GBD upper indices. Since all are written in terms of metric, it can be easily simplified. You multiply by GBD for both these terms, and then you can easily simplify this. The first term is coming out to be delta BA, and the second term is delta DD. So that is essentially the trace of an identity metric, and this is turned out to be 4, and this turning out to be delta AB. So that you have is essentially GAC minus 4 into GAC. K tensor is essentially minus 3 times K into GAB. So that is the expression for the Ricky tensor if you have Riemann tensor given by this expression. Now we compute the Ricky scalar. That means we contract this once again, that is we multiply by GAB to the RAB itself. Then we get R as a minus 3 K into delta AA. Delta AA has to be 4 in 4 dimension. That is essentially the trace of our identity metric, and that is coming out to be minus 12K. Once we computed the Ricky tensor and Ricky scalar, we can easily compute the Einstein tensor. GAB is equal to RAB minus half GABR. So you might ask why we are doing through all this exercise to show that K is constant. The only identity which we have is a divergence of Einstein tensor is 0, and that is a way to show that the K has to be constant. To find the Einstein tensor, we need both the Ricky tensor and the Ricky scalar. Once we find that, we can calculate the Einstein tensor, and that turns out to be simply minus 3 times K into GAB plus, because of the minus and minus together becomes the plus 12 by 2 into K into GAB, that is plus 3K GAB. So that is the Einstein tensor. Now we take the divergence of that and set to 0. The divergence of GAB is 0 because covariant differentiation is essentially defined like that, and that leaves out that the divergence of Einstein tensor is 0 if and only if divergence or the partial differential of a K is also 0. That means the K has to be constant, and that is what exactly we had to show. So this is how some of the properties of Einstein tensor help us to simplify the form of a specific case of Riemann tensor. So that is what we have to see. So we have a Einstein tensor defined as a 3 into GAB. Now take the divergence of that to be 0. Then the divergence of 3K GAB is equal to 0. That implies the derivative of K has to be 0, because we know that the divergence of metric tensor is 0, or even the covariant differentiation of a metric tensor is 0. So resulting in the partial differential of a K is 0. So this divergence of Einstein tensor being 0 help us to show that the K has to be constant for this specific case. However, this is a highly symmetric kind of a space, which is we will see sometime in the cosmology part of this course. Let me stop here and continue in the next video more property of Einstein tensor, and even leading to the Einstein's equation.